In this video, let's learn about Riemann sums. So Calculus 1 can be broken into two major classifications: differential calculus, which involves the use of derivatives to study the rate of change, that's what we've been doing, and integral calculus. This involves the use of integrals to study the area under a curve. This section marks the beginning of the study of integral calculus. In order to talk about integrals, we must first determine what it is we're trying to find. Once we figure out what we're trying to find, we then decide how we're going to find it. This will then have further implications, which will lead to many types of applications that involve the use of derivatives and integrals interacting together to evaluate the motion of the world around us. So the first question, what are we trying to find? And that's the area between the curve and the x-axis. And how are we going to find it? Well, let's start by looking at some examples. Suppose you want to find the area under the curve y equals 1/2 x. That's just this linear function right here. The y-intercept is 0 and the slope is 1/2. And we're looking between 0 and 6. So the first thing is start with a sketch. So you'll have a visual. So here's my line, and then if we're trying to find the area between 0 and 6, it is this right triangle. We just apply our right triangle formula. Our base is 6 and our height is 3, and so we can see that the area is 9 units squared. Sometimes the shape formed between the curve and the x-axis is a recognizable shape from geometry. Many of these shapes have area formulas that you're familiar with. We've got a trapezoid in this first example. The formula for a trapezoid, and you'll need to learn this one because we'll be doing lots of examples with trapezoids. You add the two bases. The bases are always parallel, divided by 2 times the height. So in this example, our base 1 is 3, our base 2 is 7. So 3 and 7 divided by 2 times the height. And the height is perpendicular to your bases, so we can see that the height is 4. This trapezoid is like on its side. When we evaluate this, it's 20 units squared. We've got a semicircle here, so that's pi r squared divided by 2. Our radius is 3, and so pi times 3 squared divided by 2 is 9 pi over 2 units squared. And then some shapes are a combination of shapes. We've got a rectangle here, a trapezoid in the middle, and a triangle over here. And you could have, cut this up into different shapes. It's fine. And so just apply the area formula for each of those shapes, add them together, and the final answer for this guy is 49/2 units squared. Sometimes the shape formed between the curve and the x-axis is not a recognizable shape from geometry. In these situations, you need to find the area by using other methods besides using a formula. You may not even be able to find the exact area. You may need to settle for finding the approximate area of the shape. Here's an example. We've got a parabola, y equals 4x minus x squared, right here. It says in order to approximate the area between the curve and the x-axis, we can fill up the area with shapes from geometry that you know the area formula for. The easiest shape is a rectangle. So that's what we're going to use here. Because the upper limit is curved, this guy right here is curved, using rectangles will not give us an exact area. The number of rectangles we use and the placement of these rectangles will also play into our strategy. Let's try using 4 rectangles to approximate the area. There are 3 different placements of those rectangles that we will use in calculus to approximate the area of the shape. The first is the middle rectangular approximation method, or MRAM. The next is the left rectangular approximation method, or LRAM. And then the last is the right rectangular approximation method, or RRAM. So here's the MRAM. And it says this graph approximates the area using MRAM. Since the graph crosses the x-axis at 0 and 4, we will use 4 rectangles to approximate the area. Each rectangle will have a base length of 1. The height of the rectangles will be determined by measuring from the midpoint of each base up to the function and then draw a segment across for the top of the rectangle. So if we're starting from 0, here's my first rectangle. Stops at 1, my second stops at 2, 3, and 4. And so we're going to evaluate the function at 1/2, at the midpoint. And so you're going to plug 1/2 into your function and evaluate. So 1/2 into my function, remember our function was 4x minus x squared. So 4 times 1/2 minus 1/2 squared, and that gives us 1.75. 2 minus 1/4 is 1.75. So that's the height of this first triangle. The base of this triangle is 1 unit, and so that's what these two numbers are representing. The second middle of the base, well, that would be 3/2, and evaluate the function at 3/2. That gives you 3.75. The next, I think that should be 5/2 right there, not 3/2. So if you evaluate at 5/2, and I made my correction over here, you again also get 3.75. And then the last one, this should be at 7/2. I think I used the same because these are the same heights, and I had already calculated them. But that's what you're doing. And so we find the area of each of these, add them up, and we get 11. So here's what you do. You divide the area into 4 rectangles. Find the midpoint of each rectangle, and where you hit the top is the top of the rectangle. Calculate the area of each rectangle and add them up. Each base is 1 unit, and the height depends on the function. Okay, here's the LRAM. I think I skipped too many pages. Okay, so very similar, except for this time you're coming from the left-hand side of the rectangle. So the leftmost corner of our rectangles is what's going to hit the upper limit of our curve. In this first rectangle, it hits at a height of 0. And so that's why this first area has a base of 1 unit but a height of 0, and so that's 0. This next rectangle, if we evaluate f of 1 into our function, we get 3. So my height is 3. 3 times 1. F of 2 into my function will give us a height of 4. 4 times 1. And then the last one, f of 3, will give us 3, and so that's 1 times 3. If we add those up, we get 10. So let me see, did I sum this up? Yes, on this first one, the MRAM, we had 11. On the LRAM, we have 10. We've got these areas here and here where we're missing those areas. But we also have some areas that are outside the curve. All right, our last example is the RRAM. Same thing, this time the rightmost corner of our rectangles intersects the curve. And so this graph approximates the area using the RRAM. Since the graph crosses the x-axis at 0 and 4, we're using 4 rectangles to approximate the area. Each will have the same base of 1 unit, and you evaluate the function at 1, 2, 3, and 4. And we can see that the right side, this is going to have a height of 0. We add them up, and we get 10. So the MRAM, we had 11. The LRAM and the RRAM, we had 10. Because the rectangles extended outside the area desired in some places and left off some of the area desired in others, the approximated areas are not particularly accurate, especially because these were some fairly large chunks. Because of this, we need to think about a way we can make this area approximation more accurate. We can make it more accurate by increasing the number of rectangles. This will reduce the amount of area in these extra chunks. So if we use 10 rectangles in this example, we get an approximate area of 10.56. If we use 20 rectangles in this area, we get an approximate area of 10.64. The more rectangles, the more accurate. Now, the exact area under the curve is 10 2/3. So this provides evidence that the more rectangles you use, the more accurate your approximation will be. Think of this in terms of a limit as the number of rectangles goes to infinity. So here's an example that I want you to try. Approximate the area between the function y is 1/2 x plus 1 and the x-axis from 0 to 4. Use 4 rectangles of equal bases with an LRAM, RRAM, and MRAM. Draw your rectangles on the graph provided and show all your calculations. So let's start with an LRAM. So with an LRAM, we're going to draw our rectangles that the left side is going to determine the height. And so we're going to divide into 4 equal sections, and it's already done for us. That's nice. So this first rectangle is going to have a height of f of 0, or y of 0. So I'm going to evaluate, and I get a height of 1. All right, my next rectangle will be determined right here at a x value of 1. So y of 1, and that gives me, let's see, half plus 1 is 3/2, or 1.5. Again, draw my next rectangle. It's going to intersect on the leftmost corner of that rectangle, and so this is going to be y of 2. And 2 squared is 4, half of that is 2, and so that gives me 3. And then my last rectangle right here, and so that is going to be y of 3. 3 squared is 9, half of 9 is 4.5, plus 1 is 5.5. Okay, so then we can, these are the heights, so let's find the area. So the first rectangle has a base of 1 and a height of 1. Second rectangle has a base of 1 and a height of 3/2, or 1. I'm going to go ahead and put them all in decimals just to make my life easier. Next rectangle has a height of 3 with a base of 1, and the last one has a height of 5.5. And when I add these all up, I get 11 units squared. So we have a curve. This is concave up. It's strictly increasing. With an LRAM, we can see we have all of these areas that are left off. So we can say that this is going to be an under approximation. Okay, let's try an RAM. All right, so I've already worked this one out. If we evaluate the function at 1, because this time our rectangles are going to intersect at the rightmost corner of the rectangle, and so we can see that each of these is going to be an overestimate of our actual area under the curve. So we evaluate at 1, 2, 3, and 4, add these areas up, and we get an area of 19. That's much different than the LRAM. All right, one more to try. This is our MRAM. All right, so we're going to evaluate the function at the midpoints. So the midpoint here would be 1/2, and let's see, 1.5, 2.5, and 3.5, because our rectangles, whoops, sorry, this is going to be your midpoint. Oops, I just drew that one wrong. This is the midpoint. This is where my rectangle is going to be. Go up from the middle. This is my rectangle. Nope. This is my rectangle. The height is determined by the middle. So middle, that's where you draw the top of your rectangle. Just practice with it. All right, so y of 1/2, y of 3/2, y of 5/2, and y of 7/2. And plug that into your formula, your equation. Okay, so let's see, 1/2 squared is 1/4 times 1/2 is 1/8, plus 8/8. If I change 1 into a fraction, that would be 8/8. And so add this up and we get 9/8. All right, so let's see, 3/2 squared is going to be 9/4. Half of 9/4 is 9/8 plus 8/8, 17/8. 25/4, half of that is 25/8 plus 8/8 is 33/8, and the last one is 49/4, 49/8 plus 8/8, and that is 57/8. Okay, so these are the heights, and each base of my rectangle is 1 unit. And so 1 times 9/8 plus 17/8. And all I'm doing here is, since all of the bases are 1 unit, I just factored out that common factor from each of these. I'm multiplying by 1, so it doesn't really make a difference here. But if I add these all together, this gives me 116/8 units squared. And that's the area under the curve with an MRAM. Okay, so looking back at the LRAM approximation in the examples, do you think your approximation is an under or overestimate of the actual area between the curve and the x-axis? Is the RRAM approximation an over or underestimate of the actual area, and why? So if a function is strictly increasing, so our function is strictly increasing, something like this. A left approximation, so we're going to draw our rectangles that are hitting the curve on their leftmost corner. We can see that there is area that's left out, right? All these little guys right here. And so this is going to give you an underestimate. And just take a minute and draw yourself a curve. Okay, so now if we have a function that is strictly increasing, then a right approximation, let's take a look at that. That means the rectangles are going to hit on the rightmost corner. On the rightmost corner. And so we can see that we're going to have area above the curve right here, here, and here. And so this is an overestimate. Okay, if the function is strictly decreasing this time. All right, so now our function's doing this, and we've got 2 that are decreasing. And we're looking at rectangles. A left approximation, that means we're going to hit on the left corner of our rectangle. Okay, we can see overestimate, and then hitting on the rightmost corner is going to give us an underestimate. And so this guy, overestimate and underestimate. Okay, so rectangles aren't the only shape you can use. We will be working some problems using trapezoids. So use 4 trapezoids to approximate the area between the function and the x-axis from 0 to 4. Okay, so if I draw in a trapezoid, I'm going to have my base 1 and my base 2, and this is the slanted piece, and here's my height. So this is my base 1, my base 2, this distance here, this is my height of 1 unit. And so your formula for a trapezoid is 1/2 base 1, oops, sorry, start that over, 1/2 base 1 plus base 2 times the height. Or it's also base 1 plus base 2 divided by 2 times the height. And so we can evaluate the function y of 0, 1/2 0 squared plus 1, and so that's 1, and y of 1, 1/2 1 squared plus 1, so half plus 2 halves is 3 halves. All right, so that's your base 1 and your base 2. Your bases are always parallel, so 1 plus 3 halves divided by 2 times the height, which is 1. So 3 halves divided by 2 times 1, and I'm not going to put the times 1, but I have a fraction divided by fraction, so 3 over 2 times 1 over 2 is 3/4. So the area of this first trapezoid times the height of 1 would be 3/4. Okay, and then we can draw our next trapezoid and keep going. This time our trapezoid, and you can see that the trapezoid's a much better approximation of this curve. It's not a perfect approximation, but it's much better. Okay, so this is going to be my my other base. So I don't know, I'm going to call this base 1 this time, base 2. So evaluate the function y of 2 this time. 1/2 2 squared plus 1. 4, half is 2, and so that is 3. So I'm going to use those two measurements and find my area of this second trapezoid. And so base 1, 3/2, base 2 is 3. Add those together times my height of 1 and divide by 2. So 3/2 plus 6/2 would be 9/2 divided by 2. 9/2 times 1/2, which is 9/4. And so the area of this guy is 9/4. And just continue until you have add those all up and you're done. So is this an overestimate or an underestimate? When using trapezoids, you know it's an overestimate or underestimate by looking at the concavity of the curve. Okay, so if the function is concave up, then you will have, well, if we were to draw a trapezoid, and I'm drawing a very big trapezoid, we can see that all of this area, this is an overestimate because we've got extra area there. Now, if your curve is concave down, and let's draw our trapezoid, we can see that we're missing some area right in here. And so this is an underestimate. All right, so let's try a word problem. It says the table below shows the velocity of a model train engine moving along a track for 10 seconds. Estimate the distance traveled by the engine using 10 subintervals of length 1 with an LRAM, RRAM, and trapezoids. Remember that distance is rate times time, and when you find the area of the shapes, you are multiplying the rate times the time, which gives you the distance. So the approximated area actually represents the distance traveled by the train. So we've got our points plotted. 0 is 0, so that's this guy here. 112 is this guy here. 222. And so it wants us to use an LRAM. You can think about this table visually by graphing the data. I love graphing the data. Now, if LRAM, that is where our rectangle is going to hit at the leftmost corner. So this first rectangle is going to have a height of 0. Our second rectangle will have a height of 12. Our third rectangle is going to have a height of 22. Our fourth rectangle, 10. Fifth rectangle, 5. 13. 11, 6, 2, and our last rectangle, 6. Okay, and so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's our 10 rectangles. And so find the area of each of the rectangles. The bases are each 1 unit. And the heights are just determined by these guys right here. These are all my heights. So in this case, base times height, we just need to add up all of these values. Because 1 times all of these, there it is. Okay, so when we add those all up, that is 87. And so the height is in inches per second. And because that's our velocity. So this is inches per second, and our time is seconds. So when I multiply these, this is going to give me inches traveled. And if we add these up, we get 87 inches traveled. That's the distance that this train has gone. And this is with an LRAM. All right, let's try it with an RRAM this time. And so I'm going to be starting with the furthest right. So my rectangles are these guys. All right, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's my rectangles. Again, my base is 1 unit, and I'm starting with 0 this time. So 1 times 0 plus 6 plus 2 plus 6, 7, 13 plus 5 plus 10 plus 22 plus 12. And that also gives me 87 inches. And then with the trapezoid, all right, so we're going to connect the trapezoid. The first region is going to have a base of 0. So if I were to draw a trapezoid here, it's really more of just a triangle. You'll be able to see the trapezoid in this next one, though. Here's my trapezoid. And then in the next one, base 1 and base 2. The height's all going to be 1. And we just keep connecting these, and we just add these up. And so I'll just add the first couple just to make sure everybody understands what we're doing. And so let's start with the area of the first one. So the area formula is base 1 plus base 2 divided by 2 times the height. And so in this case, my base 1 over here is 0. My base 2 is 12 divided by 2, and my height is 1 unit. And so this is going to give me 6 for that first one. Okay, so, and I can just string all of these sums together. So it's going to be 6 plus, and then the next one, base 1 is 12, base 2 is 22 divided by 2 times the height of 1, plus the next one, 22 plus 10 divided by 2 times height, plus the next one, 10 plus 5 divided by 2 times the height, plus 5 plus 13 divided by 2 times the height. And we just keep going. I'll let you finish this. Check your work. I do get 175 halves inches traveled. Okay, it is time to practice.